Hello students. In this set of videos, we're going to talk about a concept called mathematical induction. It's highly related to series and sequence, but it's a slightly departure from just calculating sum of sequences and series. In particular, mathematical induction is a method to prove a claim that involves some kind of integers n. Okay, and it turns out it's a very powerful way to prove specifically on claims that involve integers, as you'll see. So obviously we need to specify your claim, and after that the step one, which is called the base step, is to prove the claim is true for n equal to 1. Then step two, which is called the inductive step, is to prove that if the claim is true for n equal to k, then it must also be true for n equal to k plus 1. And by combining step 1 and step 2, then we can prove that the claim is true for all values of k greater than equal to 1. Okay, so let's do an example. Okay, so I've rewritten the steps of proving by induction. On the right hand side there, we begin with a claim or premise that we call P sub n. Okay, that the premise involves some kind of variable of an integer n. The step one is to prove that if Pn is true for n equal to 1, and then step two is to prove that if Pn is true for n equal to k, then it must also be true for n equal to k plus 1. And the example that I'm going to use is a fairly simple one to begin with. So we all recall the sum of an arithmetic series, and let's say I write it in a sigma notation like this. I'm using the index j. J go from 1 to n, and a fairly simple arithmetic series 2j. And we know by the sum formula that we have learned, this is going to be equal to 2 plus 2n, the first term plus the last term, multiplied by n over 2. And if I simplify this, this just becomes n times 1 plus n. Okay, so let's make a claim. Okay, my premise is for P sub n, the claim is that any series that can be described in this fashion, arithmetic series, then it must have a sum of n times 1 plus n. This is my premise. Okay? And let's go ahead to prove it using induction. So step 1 is to prove that P sub 1 is true. In other words, when equal to 1, when n is equal to 1. Is it true? Well, let's try. So summation of j from 1, n is equal to 1, so it just go from 1 to 1 of 2j. Well, that's just one term, which gives us 2, right? On the right hand side, n times 1 plus n, when n is equal to 1, that's going to be equal to 1 times 2, which is also 2. Well, obviously these two are equal, so therefore we can conclude P sub 1 is true. Okay, so we've proven that. Okay, let's go to step 2. Step 2 is to prove that if P of k is true, then P of k plus 1 must also be true. Okay, well, let's see what P of k says. So P of k means that if I'm summing from j equal to 1 to k of this series 2j, then the sum must be equal to k times 1 plus k. That's what pk states. So we take that as a given information. Okay, this is true. Assume this is true. If that is the case, then what if I add one more term to this? So summing from j equal to 1 to k plus 1. I'm adding one more k. I'm adding one more term. Okay, k plus 1. Well, that is going to be equal to the original sum, which directly comes from here, k times 1 plus k. And I'm just adding one more term to it, right? And what is that term? That term is 2 times k plus 1, right? This is the additional term that I'm adding to. Well, let's simplify this a little bit. I'm going to be factoring out this k plus 1 as a common factor, okay? So I'm going to factor out 1 plus k. And what I have left is 2 plus k. And if I rewrite this a little bit, this is going to be the same as k plus 1 times k plus 1 plus 1. And what we realize, or what you notice, is that this k plus 1 is exactly the same if I were to write my summation j equal to 1 to k plus 1. And this fits exactly my premise k plus 1, because premise k plus 1 states that the summation of this series should be k plus 1 multiplied by k plus 1 plus 1. And these two matches. So therefore, I can conclude that if p of k is true, that also implies p of k plus 1 is true. And the final conclusion is that our premise, p sub n, is true for all values of n greater than or equal to 1. Let's take a look at another example. So this one says that 4 to the power of n minus 1, that quantity is divisible by 3. So can we prove that? Well, let's first establish our premise. So we're going to write our premise or claim p sub n states that 4 to the power of n minus 1 is divisible by 3. Okay, this is our claim. It seems pretty obvious, but sometimes it's a little bit different from what we're trying to prove. In this case, you can use the original claim as our premise. So what are the steps? There are two steps. Step 1, is indicated to the right, is to prove that Pn is true when n is equal to 1. Well, is it true when n is equal to 1? Well, let's see, 4 to the power of 1 minus 1, that is equal to 3. And obviously, that is divisible by 3. So therefore, p sub 1 is true. Step 2 is to prove that if p sub k is true, then p sub k plus 1 is also true. So we'll start with p sub k. P sub k would state that 4 to the power of k minus 1 is divisible by 3. Okay, so that is a given. Okay, we're given that this is true. Now what about p sub k plus 1? Well, that means I have the quantity 4 to the power of k plus 1 minus 1. And let's see if this is divisible by 3. Well, I'm going to rewrite this by taking out 4 times 4 to the k minus 1. I'm going to do another algebraic manipulation. I'm going to somehow get a negative 4 in the second term. So I'm going to have 4 times 4 to the k. I want to subtract 4, but I want to end up with a negative 1, so I have to add 3 to make sure the expression is still the same value as before. But by doing this, this is going to allow me to write 4 times the quantity 4 to the power of k minus 1. Okay, that's the first term, plus 3. Now let's take a look at each individual term by itself. We're given that this expression is divisible by 3. That's given, right? So that means this is divisible by 3. Well, a quantity that's divisible by 3 multiplied by any integer is still divisible by 3, right? So that means this whole thing is divisible by 3. 3 obviously is also divisible by 3. And when you have a sum of two quantities that are divisible by 3, that means this whole thing is also divisible by 3. Okay? So therefore, we can conclude that P of k is true, would automatically means that P sub k plus 1 is also true. So therefore, we can draw the final conclusion. P sub n, which is our premise, is true for all n greater than equal to 1.